Okay, so first I'd like to thank Barbara and Philippe for inviting me here today. I've been spending all my time for the last several years sort of being a salesman and a manager and a systems engineer, and actually coming to listen to science for a couple of days is a real treat. So someday I hope to get back to some science, and this is the vehicle that I hope will take me there. This is the spacecraft for the InSight mission, which is going to Mars to do a geophysical exploration of the interior. Over the side here, you can see some of our major partners, and you can see that this is a very international mission. It's a NASA mission, but we have a very strong participation by countries other than the United States. If you look real closely, you might find your favorite institution there. So first I'd like to give credit to the rest of the science team. I mean, I'm the author of this particular talk, but the ideas behind this mission and the implementation couldn't have been done without the help of the science team and also the technical team, which would take 5 or 6 of these view graphs, so I'll have to skip that. So first I wanted to get a little historical perspective and looking at sort of the geophysical investigation of other planets and kind of particularly the seismic investigation, because if you're a geophysicist, the seismic data is kind of the gold standard. Even if you're a sort of dyed-in-the-wool gravity topography analyst like me, you really can't get away from wishing you had some seismic data to actually pin down the real structure of the inside of the planet, instead of all these theoretical ones that you can move your parameters around all the time. So, and this was well understood that at the beginning of the space age, back in the 60s, in fact, the first spacecraft that were sent to another planet, which were these Rangers 3 through 5 in 1962, had seismometers on them. They were going to the moon, and they had seismometers that had these balsa wood spheres around them that were supposed to absorb the shock, and they were then operate on the surface. But unfortunately, all 3 of these went off in different directions and never actually got close to the moon. So we had to wait for a few more years for the Apollo program in 69 through 77, which brought seismometers to the moon, and as you saw in several of the talks earlier today, got some excellent data on the interior that's still paying off. The next logical step then was to send a seismometer to Mars to do the same kind of analyses. And the first landers we sent to Mars, the Viking missions in 75, carried seismometers. And so, and this was all, so this is like the first, 15 years or so of the space, of the space age. And we were, clearly, marching down the path of geophysically investigating the planets of the solar system. So anyway, here's Viking in 1977. And then for 35 years, we haven't actually had another seismometer on another planet. So this has been a long dry spell. And we've had lots of mission proposals, even some of these missions which actually were funded for a while. Most of them were canceled, like Measure, Netlander, Humboldt on ExoMars. Mars 96 actually launched towards Mars, and it got about 800 kilometers before it fell back down. But so we've had a long time of waiting to do a real, detailed investigation of the interior of another planet until now, which we now have the InSight mission, which was selected about 2 years ago to go to Mars with some geophysical instrumentation. So the science goal of this mission, and when you start writing proposals to spend $500 million, you have to turn into a very good salesman, because it's kind of a hard sell. But we did manage to sell doing geophysics on Mars. I wouldn't actually say it's on the cheap, because $500 million isn't cheap, but it's relatively inexpensive by terms of planetary missions. So we said we wanted to understand the formation and evolution of terrestrial planets through investigation of the interior structure and processes of Mars. And we would do that using seismology, geodesy, or specifically the rotational geodesy of the planet, and heat flow. And we sold this not as a Mars mission, that we just wanted to understand, what the interior structure of Mars is just out of random curiosity, but that we could use this as a laboratory for understanding the processes that form all rocky planets, all the rocky planets of our solar system, and by extension exoplanets. And we argued that Mars was particularly well suited to doing this kind of an investigation. First of all, because it appears to have maintained the structure soon after differentiation for the last 4+ billion years. We have evidence that we have reservoirs that have persisted, as Doris was talking about. We have a cratering record on the surface, which covers the entire surface, that dates that surface back to more than 4 billion years ago. And so the crust hasn't been disrupted in a large sense since the very earliest Noachian. And then we have some sort of bonus points for having a surface that's more accessible than some of the other planets we might go to. Venus would be a great planet to investigate and compare with the Earth's structure, but it's a little bit difficult to survive on the surface. Mercury's hard to get to. And we have because of the fact that Mars has been a focus of space exploration for the U.S. and Europe, for that matter, for the last 20 years. I think we've sent more than a dozen spacecraft to Mars in the last two decades. We actually have a really comprehensive store of information about the surface, not very much about the interior, but about the surface, that provides a really good context for interpreting our measurements of the deep interior of Mars. And so it's actually a pretty good place to do some of this testing. So what are some of the questions that we can answer with a relatively coarse and simple investigation of the interior? So when you think about seismology today, it's very different than what you're going to see from InSight. Seismologists today use massive data sets and very high signal noise records and many different records and do a lot of sophisticated inversions. And we're going to go to Mars with one seismometer, actually 6 seismometers, but they're all in one place, so it doesn't really count. And we're going to be doing a little bit different kind of seismology. So we want to be able to answer questions with fairly coarse measurements, things like the thickness of the crust, for example. From orbital measurements, we know a lot about variations in the thickness of the crust of Mars from gravity and topography measurements, but we don't know the average thickness of the crust. So we don't know the actual volume of the crust to probably within a factor of 2. I mean, you can make some arguments based on theoretical considerations, but really in terms of actually knowing a number, I'd say a factor of 2 might even be a little bit on the low side. So we would like to know that's going to give us a lot of information. Is the crust layered? Do we have different layers of the crust, a primary crust that may be covered up by a secondary crust? Is this the result of differentiation, primary differentiation, or a late stage overturn? All these things can be answered by a simple thickness measurement. If we get one good thickness measurement of the crust, we can answer a lot of these questions, or at least start asking some more interesting questions. In terms of the mantle, we would like to obviously know what the actual composition is, not the mineralogical composition to some extent, whether there's a stratification, whether there's layering, what the density profile looks like, all the kinds of things that Doris was talking about just in the last talk. We'd like to know the thermal state of the mantle, whether it's a hot mantle, a cold mantle, whether it's got a steep gradients or not, whether it's convecting, obviously. And some of these questions can be addressed, at least to some extent, by some basic seismic observations. And finally, we'd like to understand a little bit more about the core. We know something about the core of Mars from the measurement of its moment of inertia and the bulk density of Mars. but there's still that's a pretty thin data set to go on for the kinds of questions that we'd like to be answering. We are pretty sure now that the outer core, at least, of Mars is liquid from some geodetic measurements from orbit, but we certainly don't know whether there's a solid inner core. The density and the radius are uncertain to something like 15%, which makes it very difficult to sort of pin down what the composition of the core is. You know, how much other elements are there in the core besides just iron. There's an interesting fact that the perovskite phase transition occurs right about where the middle of range of possible core radii are. So this could either be actually existing in the mantle, or it could be, you know, buried in the in what's actually the core, so it may never actually manifest itself in the mantle, and this can have a big effect on the lower boundary condition in terms of heat transport. So we would like to be able to, obviously, just to measure the density of the core. Just that one number would go a long way towards answering a lot of our questions about core formation and the thermal history of Mars. Okay, so the sort of our postulate for this mission is that the basic structure of Mars, things like you know, a handful of parameters, will provide key information about the formation and evolution of terrestrial planets, of Mars in particular, and terrestrial planets in general. And we've already gone through a lot of these things. We want to be able to get the thickness of the crust, and if possible, sort of large-scale layering. For the mantle, we'd like to know about its overall composition and thermal properties. For the core, its size and density, and of course the state being whether we have a complete liquid core, a solid inner core or not, will provide us with a lot of information. And these parameters we've mapped straight into what we call the level 1 requirements for the InSight mission. And these are the things that we've promised, you know, NASA, that if you hand us this big check, we'll deliver on all of these on all these promises. And these are, like I said, we just have a handful of parameters here that we've signed up to do. We have crustal thickness, large scale layering in the crust, seismic velocities in the upper mantle, and we have error bounds on all of these that we believe that we can meet with our systems. Liquid versus solid outer core, radius, density of the core, and the heat flux from the planet. And sort of as a bonus, we can actually also measure the geologic activity and the rate of meteorite impacts on the planet, and do some geographical distribution of that as well. So that's also of interest to geophysicists and geologists. So what do we actually know about the interior of Mars? And I would contend that we don't know very much. In fact, when I first started, you know, kind of working seriously on Martian tectonic problems, tectonic modeling back in the 70s, we don't know a whole lot more about the interior, deep interior of Mars than we did then. We have information from the S&C meteorites, which has given us a lot of sort of general information that we can use for geochemical and mineralogical modeling, but in terms of actual measurements of the interior of Mars, we have a few rotational measurements that have given us some information, but other than that, we're still waiting on a lot of this information. So, like I said, we have about a factor of 2 uncertainty in the crustal thickness. We don't know anything about the crustal layering. We can infer a mantle velocity structure from just analogy to the Earth. So I'd say, you know, we kind of know it more or less to plus or minus a kilometers per second, but that might even be optimistic. We are pretty sure that it's liquid from some measurements, but it's still a little bit uncertain. We have a big uncertainty in the radius and the density of the core. The heat flow is mostly just a guess. That's really a range of models that doesn't really have too much to do with measurements. And we certainly don't know the seismic activity to within a factor of 100, which makes it a little bit little bit dicey going on there for a seismological mission, but I think we got a good story there. So, and then what can we do with insight? And we've gone through the analysis of the kinds of measurements that we can make, the techniques that we can use, and the errors involved in all these, and we've come up with a capability listed in this column, and we can see that the improvement is pretty substantial in all these parameters. And like I said, even something like this, I say 7.5 times. Really, it's a brand new measurement, and so we have the ability to make quite a substantial stride in all these measurements. And I would say that these are somewhat conservative numbers too, because we had to back all this up with analysis in the proposal. And I think, you know, when we really start looking at a good data set and bring all the ingenuity of the scientific community to bear on this data, we'll probably do better than that. So a little bit about the mission. So we're flying a near copy of the Phoenix lander, which went to Mars in 2007. We're launching in March 2016 from Vandenberg Air Force Base, and just so you know, that's 15 months, 13 days, and 20 hours from now, for those of you who are keeping track. We have a fast trajectory to Mars. It only takes us 6 months, which is pretty good for Mars missions, and so we'll be landing in September of 2016. We have about a 2-month deployment phase where we actually put the instruments on the ground. I'll talk a little bit more about that. And then our nominal mission is 1 Mars year, which is almost exactly 2 Earth years on the surface, doing basically passive measurements of seismic activity, heat flow, and rotational variations, with a nominal end of mission in 2018. So one cool thing about this is that we're actually launching from California. So instead of Florida with alligators, we have a much cuter animal that sort of represents our launch. So it's going to be really fun, especially since the mission is based in California. It saves us from doing a lot of traveling. So here's our spacecraft. It's actually, you may think it's easy to land on Mars, but it's actually really difficult. And one of the reasons it's difficult is you really need 3 different vehicles in one. It's sort of a Transformers thing, where you have to be able to fly to Mars as a sort of an interplanetary spacecraft, and this is what we look like in the cruise phase, all buckled up, buttoned up inside of a heat shield, an aeroshell with some solar panels. This whole business here is ejected before you hit the top of the atmosphere. You slow down somewhat just using the heat shield in the front, and then you put out a parachute, and finally about 4 kilometers above the surface, you cut this cord and eject that cover, and you go into this mode here. So you have this guy here where you're just flying through space for 6 months. Then you have to have an entry and landing system, which is sort of these 2 things here. It lands actually on a set of rockets, much like Viking did, not so much like Curiosity or Spirit and Opportunity. So JPL doesn't ever like to do the same thing twice, so we had to really work hard to get this guy going. And finally, you have to land on the surface and survive there for several years. And Mars is a pretty harsh environment, so that's very challenging all in and of itself. And so having one vehicle that sort of does all these things is pretty amazing. Okay, so our payload was sold to be relatively simple. We only have 2 instruments on this mission. We have a seismometer and a heat flow probe, and then we have a radio tracking system from the communication system that allows us to do our geodesy. But when you start looking below the surface, it's a little bit more complicated than that. So here's our seismometer. It's being built by CNES, a French space agency, with partners in Switzerland, Germany, and the UK. We have the sensor head here, which has 3 very broadband seismometers. So we have a triaxial measurement. They're extremely sensitive. We also have 3 short period seismometers, which are MEMS devices that extend our frequency range from up to several tens of hertz. We also have, and then we have the electronics which sits inside the spacecraft. It's connected to the seismometer through this tether, which has about 200 wires going through it to do the communication with the seismometer. And we have this thing here, which is our wind and thermal shield. And I'll just speed this up, maybe start here. So one thing that we want to do is be able to protect the seismometer, so we developed this device here with a hard shield and sort of a flexible skirt, which can then seal around the seismometer and keep the wind from impinging on it and keep it thermally relatively stable. So that's what we have instead of the standard, seismic vault in the basement of your science building. Okay, so in addition to the seismometer, we have our second instrument, which is called HP Cube, which stands for Heat Flow and Physical Properties Probe, and it has a mole which digs down into the soil and drags a tether behind it. It's supposed to penetrate down up to 5 meters below the soil and measure the gradient and the thermal conductivity. It also has a radiometer that looks at the ground next to the spacecraft and gets the temperature. And our third investigation is the geodesy or RISE experiment. It uses the X-band transceiver on the spacecraft to track its location in inertial space, and by doing that over a period of time, we can watch the planet rotate and watch the variation in the pole position. We have an auxiliary payload suite, which measures some of the environmental factors which will impinge on the seismometer. We have a magnetometer, a pressure gauge, and a set of wind sensors. And finally, we have a deployment system to put these things down on the surface, which consists of an arm, which was actually already built for a mission that was supposed to fly in 2001, but was canceled. And so this has been sitting in a closet at JPL for the last 12 years or so, and we were able to get it very cheap. And a set of cameras, which are also sort of leftover spares from previous Mars rover missions. We're going to be landing in a place called the Western Elysian Planitia. It actually turns out to be only a few hundred kilometers away from Grail Crater, where Curiosity landed. It turns out just the logistics of landing and operating on Mars sort of drove us to this region here. Mars is a big place, but as far as InSight concerned, it's actually pretty small. We only had 2 or 3 places that we could even consider landing. And this actually turns out to be a pain in the neck, because we communicate through orbiters, and when an orbiter goes over Curiosity, it's also going over us, and so we're going to be contending for bandwidth on the relay for our entire mission. But that's sort of what we're stuck with. So within that region, we identified a set of landing ellipses, and these are sort of probabilistic regions in which the lander could end up. There's a certain amount of dispersion just from errors in the trajectory, and also mostly from the effect of variations in atmospheric density as it comes in. And so these are about 120 or so kilometers long and about 35 kilometers wide, and we need to eventually to find one of these which is essentially flat and almost rock-free over most of its area in order to land our spacecraft. And NASA likes to see probabilities of success in these things on the order of about 97 to 98%. So that means you can only have about 3% of regions within that ellipse which have either craters or rocks or something else. And we're looking at those very detailed from HiRISE, the high-resolution camera on the Mars Reconnaissance Orbiter. We've narrowed it down to these 4 ellipses up at the top. We're trying to get it down to 1 ellipse by next summer. And so we will be landing somewhere in this little range here, which is kind of this upper corner of this rectangle on Mars. So one of the questions that we're often asked is how do we expect to do seismology and actually get information about the interior of the planet with only 1 seismometer? And we've put a lot of thought into that, and it turns out seismologists are actually really good at using single station data. They just don't do it very often because they can get better data by using lots of stations, but the techniques actually exist. And sort of our bread and butter technique for actually getting the kind of seismic data that you get from the Earth is taking advantage of the fact that Mars is a very small planet, and so surface wave propagation, because it has a relatively small surface area, is pretty efficient. And in fact, we can use to our advantage the fact that not only do we have P and S waves that travel more or less directly from an event to our station, giving us 2 arrival times, we also get a Rayleigh wave that travels from the event to the station, the short wave around the planet. We have another one that comes in a little bit later, the R2 Rayleigh wave, the other way around the planet. And then we actually have a third arrival, which is the R1, which then goes all the way around the planet and hits the receiver again. So we actually, but in that case, we can determine precisely the distance to the event from our station, and even use polarization techniques to get the back azimuth as well. And so we can do event location on Mars with one seismometer, where most of you, when you took your first geophysics course, they taught you need 3 or 4 seismometers to do triangulation. Well, there are ways around that if you get clever, and the idea is to put together a travel time, a family of travel time curves like this that you can then invert into your structure. Okay. We have other techniques we can use, receiver functions, which are good at giving us crustal information, and also surface wave dispersion at lower frequencies and requiring somewhat larger events. We can perhaps get some information from normal modes, or even the normal modes that are excited perhaps by atmospheric excitation. So we've done some simulations using Earth data on how well we can do on Mars. So we took a single station in Black Forest in Germany and took a set of 36 earthquakes that were scaled appropriately to be able to get those kinds of multiple surface wave arrivals for the Earth. They're bigger than what we expect on Mars, but we have to pick bigger ones to use on the Earth. And then did the analysis the way we intend to do it on Mars, just on that one station's worth of data. And these curves here, the black dots, are the actual locations of these quakes from the catalog, and the red symbols are our calculation of the locations using our technique. And you can see that we have a pretty good agreement, and these are the curves that you can generate from a PREM model. We then went ahead and inverted that data using for the velocities in the crust and upper mantle. The gray band here is the uncertainty range that we signed up to, plus or minus 5% in our proposal. The black line is the actual PREM model, and these colored lines are the models that we get using 7 of those events at a time. We broke up that data set into 7 independent data sets, because we thought sort of a conservative estimate, we should get about of the order of 10 Mars quakes that have multiple surface wave arrivals in our 2 years. And so this shows us that we can actually determine the VS and VP to a pretty good accuracy, and be able to get some pretty good constraints on the profile in the mantle. We also did a similar kind of exercise using the surface wave dispersion between R1 and R3 for those models, and show we can get a good estimate of the crust. This is the actual Earth model here, and these are our models that were run on synthetic Mars data. The second question we use is, how do you know you're going to see any Mars quakes? And there's actually about 3 or 4 different ways that you can estimate the activity of Mars. Probably the most powerful one is just saying, well, it's going to be more than the moon, and it's going to be less than the Earth. So here's the moon curve. Here's the curve for the continents on the Earth, and so we expect it in here. You can do more sophisticated analysis using faults that you can see on the surface of Mars. The dates on those faults can be determined from crater curves, and you can then sort of estimate the decline in activity through time over the last 3 billion years or so, and extrapolate that to the present. And you get a sort of a band of expected, this is the number of quakes versus the seismic moment, which is the amount of energy in the quake. This is sort of a rough equivalent magnitude up here, so you can see you have fewer quakes at higher, larger quakes are fewer, and we get a band in here somewhere. And within this band, we've determined we can see somewhere between, like I said, a dozen and maybe a few hundred Mars quakes per year that'll be useful for us. But even if we don't get Mars quakes, we have signals from other sources. We have a Phobos tide. Phobos goes overhead about every 5.5 hours and produces about 5 to 7 millimeters of ground displacement. And it's very difficult to measure, but since it goes over your head over and over and over again, we can actually start to use stacking techniques to knock that noise down and get information about the Love number from that. We can also use meteorite impacts. We expect to see something like a dozen meteorite impacts on our seismometer from relatively far away. And finally, we might be able to use just the pressure excitation from the atmosphere, which is going to pump energy into the surface to get some information that way from the normal modes. Okay. I'll just skip through this. We have a bunch of environmental sensors, as I said, because the seismometer is extremely delicate. We've done some fluid dynamical modeling over that windshield to show that it not only will keep the wind off of us, but it won't blow away. The radio tracking will give us information about variations in the rotational axis on several time scales. One is the precession time scale, which is about 165,000 years, and then also the nutation time scale, which is sort of less than a Mars year in frequency. And with 2 years of tracking, we should not only be able to get the moment of inertia from the precession rate, but actually the core moment of inertia independently from the nutation amplitude. And we do that by tracking the location in inertial space to something like 5 to 10 centimeter accuracy. Our heat flow probe, like I said, we have a self-hammering mole that can dig down to about 5 meters, and it pulls behind it a tether which has temperature sensors attached. We have a heater within the mole which can heat up the outer hull. We can then use the decay in that in temperature to get the thermal conductivity in between the two of those. We can make the actual heat flux measurement. We expect a variation over the surface, but even a measurement at one location that's well known will be able to extrapolate to the rest of the surface and get some idea about whether we have a lot of heat or not much heat coming out of the planet. And finally, I just wanted to emphasize, how important it is to do the deployment. This is sort of what sets apart this particular mission from some of the other proposals that have been done. In fact, Viking had the seismometer sitting up here on the deck. The ground's over here, and ideally, you'd kind of like to have both of them together at the same place, since that's what you're trying to measure. On InSight, that's what we're going to do. And got an animation here that runs for about a minute. Shows us how we're going to pick up the seismometer off the deck, put it out onto the surface using this robotic arm. It has a camera mounted here, so we can actually use that arm to point the camera, and we'll be mapping out this whole area here for obstacles and slopes and things like that. Once we get the seismometer down on the surface, we stop to take some pictures, and then we'll go back, and all this cable is coiled up inside this tether box here, so we'll release that to release any tension on that cable. Once that's done, we'll go back to the deck again, pick up the wind and thermal shield here, and place it over the seismometer. And again, you can see that it has this sort of fabric skirt that was made of about 4 different layers. We have Kapton around it to sort of keep the wind out, and we have actual chainmail at the bottom, just like on the old medieval armor, to mold itself around any rocks that it might encounter around the rim of the seismometer. And so that device should keep it nice and snug on the Martian surface. Once we're done with that, we do our final deployment, which is taking the heat flow probe out here It has a sort of a vertical chimney that contains the mole, and then a box behind it that contains the tether which connects it to it. Its electronics. You can also see the medium gain antennas here and here, which will be used for the Doppler tracking of the spacecraft back to Earth. And we have our wind sensors here and here. The pressure inlet is there. And once we do this final deployment, as I said, this whole process that took about a minute and a half actually takes about 65 days or so on the surface of Mars. So it's a very slow operation, but in the end, we'll have our instruments on the ground. And that's pretty much the end of the talk. I just ended up with a quote from Einstein, which I thought was pretty apropos for looking deep into nature, into the planets. But just for good measure, I also got the same message from a Chinese fortune cookie. So thanks.